And last two lectures were devoted to making some connection between this formalism of matrices and real world, including shallow water, billiards, quantum dots. Then I have shown how it is possible to measure level statistics and eigenfunction statistics in quantum dots, for instance, and it was really a big subject in the beginning of 2000. Then I discussed some other examples like microwave billiards, a little less about complex nuclei, and then I told that the region of applicability of classical random matrices is the situation where localization effects are absolutely absent, and where there is invariance with respect to rotation of the basis of matrices. Then we discussed the probability distribution of entries of Gaussian random matrix ensemble, the simplest one, and then I derived, I gave you so-called Pullman derivation of the level repulsion, and then we discussed Anderson localization in different situations, and in particular the fact that there's no basis invariance for Anderson in case there is some localization, because it is always possible to make an extended state by a linear combination of localized, and this is actually equivalent to rotation of the basis, and therefore by rotation of the basis you always can make extended state out of the localized, and then there is a question about how to describe localization effects. I told you about Anderson model in 1, 2, and 3 dimensions, then about the difference between the situation where there is localization and when there is no localization. In particular, I discussed Wigner-Dyson distribution with level repulsion and Poisson distribution. And then I have shown you the pictures, actually old ones, about distribution of spacing in deep metal, in deep insulator, and at the critical point in 3 dimensions. Actually such curves helps to identify the critical point numerically. This is an example of that. And then also, and then I have shown you a spectacular picture of energy level spaghetti as a function of the amplitude of disorder, and it is clearly seen how the pattern of avoided level crossing here passes to the pattern of exact crossing, so Wigner-Dyson distribution and Poisson distribution, and there is something in between, which is the critical statistics, and then I have shown you the most well-known examples of how to break the basis invariance and thereby construct random matrices which model localization, which possess some sort of localization effects, and so we discussed the simplest thing of Gaussian matrices, but with the variance that depends on the entry, and so we discussed simplest thing is the Wigner-Dyson case. Then another extreme is diagonal random matrices, so banded random matrices which are equivalent to localization. And then we discussed briefly another simple example of Rosenzweig-Porter matrix, which is a sum of the Wigner-Dyson matrix and the random diagonal matrix. So the special diagonal, this special diagonal breaks basis rotation invariance and allows for localization effects. I think we will be discussing in more detail this. Then there is another famous example of power law-banded matrices where the variance depends in this way. So it does not, there are two parameters A and B, and A is a parameter that drives from delocalized to localized situation, and there is A equal 1, which corresponds to critical statistics of everything of wave function of the spectrum. And this, since there are two parameters, when I set A equal 1, there is still B, and this B is a parameter that controls the strength of localization effects, and actually this model is very close to the Anderson model, and it is possible by identifying the proper parameter B, make statistics of wave function statistics of eigenvalues not only qualitatively but quantitatively similar to the one in 3D Anderson. But then I told you about some peculiar model which looks a bit, too complicated. But essentially this model, on the average, it behaves like power law banded matrices, but possesses some hierarchical structure of variances, and this model is, in my opinion, is understudied, and there are some results. Our recent result, for instance, with a group of Vladimir, which show that this is probably the cleanest model which describes hierarchical structure of critical states. So in 3D Anderson model and in power law banded matrices, it is a bit spoiled by some features of the model, and here it looks like we have this hierarchical structure in a clean way. So I hope we will discuss later this thing. And today, I'm coming to very well-known material, textbook material, but still it is in the core of this theory, and I have to do it. So first of all, now we consider the conventional Wigner-Dyson model. So for simplicity, I take this coefficient equal to 1. This is not the same A as was on the previous slide. This is simply the scale of the energy. So by changing the scale of the energy, you can change this A. So, and as I have shown before, this distribution of entries is manifest invariant under rotation of the basis, because if you put decomposition of H by eigenvectors, this is unitary matrix made of eigenvectors, and this is the diagonal matrix of eigenvalues. So if I put it here, then because of the trace, this thing cancel out, because of trace allows to do cyclic permutation, and U drops out of this expression, and I will get very simple thing. So what I will get is simply trace of E squared, and this trace of E squared is nothing like this thing. So, but this is not the end of the story, because this is the most trivial part of the story. And the non-trivial part of the story is that when I switch from the variables which are entries of this matrix to the variables which are eigenvectors in this unitary matrix and eigenvalues in this diagonal matrix, then I have to compute with Jacobian. And now I just explain how to compute the Jacobian, because you know, this is a not very simple decomposition. So, but there is very simple way to compute Jacobians of any decomposition like this. Of course, I will not prove mathematical theorems, but I give you the recipe how to do it. And so the recipe is well illustrated by computing Jacobian from Cartesian coordinates x and y to radius and angle, just in two-dimensional space. And this is very good illustration of what I will do then in a more complicated situation. So what you have to do, you have some function of x and y, and then you have the measure, which is dx, dy. And you want to instead use the polar coordinates in which x is r cosine theta and y is r sine theta, and I will show you how to do it in some very simple way. Of course, this is a simple example. You can do it in zillions of other ways, but one way is very simple. So what you do, you take what is called the Cartesian interval. So the sum of dx squared plus dy squared. Okay, so we know that x is r cosine theta and y is r sine theta. So I differentiate this guy and this guy. So in order to find dx, I differentiate. I say dx is dr times cosine theta minus sine theta minus sine theta dr, d theta times r, and the same way here, and I substitute it here and there, and then make simple algebra. And what I obtain two remarkable things. So one thing is that there is no cross term d theta dr. There is only d theta squared and dr squared, and the cross term cancels out. And then there is something in front of d theta squared and unity in front of dr squared. And the theorem, which I am not going to to describe, to prove here is the following, that in order to find determinant, in order to find Jacobian, you have to look at this result as a quadratic form. And it is indeed a quadratic form without the cross term. Now, you write this quadratic form as a matrix. So you see here there is r squared. Here there is 1. Here there is 0. Here there is 0. So this is a matrix of the quadratic form. So if I multiply it by the vector d theta dr from this side and from that side, I will get this quadratic form. But what I'm interested in this matrix. So then you have to compute the determinant of this matrix. So here the determinant is very simple because there is no cross term. But even if there are cross terms, it is still valid. So you just compute the determinant of this, and this determinant is given here, and then your Jacobian will be just a square root of this determinant. So it will be determinant is r squared, square root of r squared is r. And this is very well known result for polar coordinates in 2 dimensions. But if you have 3 dimensions, 4 dimensions, whatever, you can act in the same way. It is only that there will be more angles but the recipe is one and the same. So you just compute this form, look at it as a quadratic form, find the matrix of this quadratic form, and find determinant of it, and then take a square root. So now let's do.
This theorem works for any unitary transformation?
It works for any transformation of that type, so to say. I mean, if there is any transformation of that type, it works. Now, what we have to do, we have to do the same for the case where your h is represented in this way. So this E will be analogous to radius, and eigenvectors are hidden here, and the angles, so to say, they are made of eigenvectors. So, but what you do the following: you just find the trace of dh squared. So you differentiate dh, differentiate with respect to elements of u, with respect to elements of e, and then take the trace of dh squared. So I leave it for you to do this simple operation, and then you introduce d, and instead of angles here, you will have a matrix like this. Either in this form or in that form, and these are the right variables for eigenvectors. So if you introduce such variables df, and this matrix is anti-unitary, so if I take if I take F dagger instead of D, because the U is the unitary matrix, this matrix is anti-unitary. So then you see, you should know only what are the right variables. The right variables are dE and the right variables are dF. And then you just straightforwardly differentiate, substitute to here, like we did with this thing. And then what you will get this expression. So I invite you at home to do this simple exercise, and what we see here the following, that there is dE squared, and there is dF squared, and there is dF dx. F is a matrix, and therefore we cannot, it doesn't compute with the diagonal matrix. So we have to respect the lack of commutation here. And but what is common with the example of two-dimensional case, polar coordinates, that there is no cross term. So here there is no term d theta dr, and here there is no term dE dF, and there is only the dF dF and dE squared. Now, of course, I can represent it. I introduce matrix indices and write this stuff in this form, and then what I see that it is also like a quadratic form, but instead of r squared here, there is this difference, and here also coefficient is equal to 1. And so what I have to do, I have to compute the determinant of the matrix of this form, and this matrix is like this: E1 minus E2 squared, E2 minus E3 squared, and so on. So this will be this part of the matrix, and then there are n unities, because here the coefficient is 1. And now you have to compute the determinant of that. And the determinant of that is actually if dF is a real matrix, so it is when your Hamiltonian is real, then eigenvectors are also real, and this is a real matrix, a real antisymmetric matrix. And when it is real, so this is only one number, dF and m squared, not without the modulus. One number in the sense that, of course, not one, but one for any given n and m. And the determinant is like I have written here. And then when we compute this determinant, it will be the sum of such difference, the product of such differences, and the product of 1 is 1. So what you have, your determinant will be the product n greater than m, ei en minus em squared, and this will be the determinant. Now you have to take a square root of it, like in that recipe. And then, of course, the Jacobian is always positive, therefore you take the positive root of this, and what you have, n greater than m, modulus em minus em. So this is in case where the Hamiltonian is real. Now, when the Hamiltonian is complex, then the number of these variables doubles, because there is a real part of f df and the imaginary part of df. And so I will have the double set of these things. So I have this product up to and then I have the similar set E1 minus E2 squared and so on. And because this coefficient does not is the same in front of the real part and in front of the imaginary part. And what will happen is that the Jacobian will be raised not to the second but to the fourth power, because there is 2 times E1 minus E2 squared, 2 times E2 minus E3 squared, and so on. And then when I take the square root, there will be 2 here. So if we have a real Hamiltonian, we have Jacobian like this. If we have a complex Hamiltonian, we have a Jacobian like that. And then, when we know this Jacobian, we can write we can collect everything. So we can collect this trivial part when we substituted this decomposition to here, and then the Jacobian. And that is the joint distribution of energy levels. So we see that this joint distribution does not depend on the eigenfunction or whatsoever. It depends only on the eigenvalues, and this is because this coefficient here does not depend on eigenfunction, doesn't depend on f, it depends only on E. And this is just unity. So we have a distribution that does not depend on eigenvectors, and this is essentially the property that can be traced back to the invariance with respect to basis rotation. So now, if we look at this stuff, we see that if En minus Em is small, then you always have a linear term here, and you have a quadratic term there, and it is what we already seen as level repulsion in this simple derivation that I gave you before. But this is a general derivation. This contains all the eigenvalues, and we will be using it to do much more rigorous calculation. So this is some stuff. This trick of computing Jacobians is useful in many calculations, not only here. That's why I have shown it to you. And now we come to very important thing, because the power of Linear-Dyson theory is actually twofold. It is powerful because there is a separation between eigenvalues and eigenfunctions, and the distribution of eigenvalues does not depend on eigenfunction. It is powerful in other way because actually it is controlled by the time reversal symmetry or the lack of the time reversal symmetry. So, and now I just want to give you some piece of formal thing which shows how this symmetry works. So first of all, we start from time reversal operator. So the time reversal operator applied twice, that is t squared, should bring your state to the initial one. So if you apply only once, you may get a different state. But if you go back and then go forth and then back, then you will have the same state. And but we know that quantum mechanical state is defined up to a phase factor. And therefore, applying twice time reversal symmetry, you just have unity, which means that it is the same, essentially the same state, and the phase factor, which modulus is equal to 1. So this is the definition, simple definition of time reversal operator. And now, it appears that there are two types of time reversal symmetry. In elementary quantum mechanics, what we know about time reversal symmetry is that if you complex conjugate your wave functions, this means you applied time reversal operator. But this is only when your wave function is a scalar. But we know that there are spinors, and then the time reversal operator must be a matrix that does something to this spinor. And so we, in general, define time reversal operator as the complex conjugation times some matrix that act on the spinor degrees of freedom. And now we substitute it here, write Kc, t squared. It should be equal to alpha times unity operator, but the combination CKC simply makes this guy complex conjugated, and then C disappears, cancels out. So it makes only complex conjugation of this matrix. So therefore, there is one relation like this. Now, then we know that time reversal operator should leave the wave function normalized, so it should be a unitary operator. And then the definition of the unitary operator is that k times k dagger, which is complex conjugated and transformed, is equal to 1. And then I can make this relation transformed, and when I transform it, I will get the relation like this. Now I can express k conjugated in terms of K transformed, and this is such simple relationship, and this is equivalent to the definition of the unitary operator. So if it is a unitary operator, then this is also true. Now, what is the goal of all this manipulation is to show that this alpha has only two possible values. So in the beginning, it could be any phase factor, EI theta. But in the end, we will see that it has only two values, +1 and -1. And in order to show that, what I do, I use first this relationship and write K as alpha times K complex conjugated -1. This follows from this relationship. Now, then I use this relationship and write instead of that K transform. And then I use this relationship second time. So I write K equal alpha K transformed and substitute it here and make another transformation. So I simply, instead of K here, I write K equal this thing, and then I transform this K. And what I get then is that it is alpha squared, and K transformed is K. So what I obtain that the operator K is equal to alpha squared times K. And this is alpha squared, not modulus alpha squared. This is the important point. By combining this definition or the property, if you wish, and the unitarity of K, I am expressing K in terms of the K itself, but alpha squared in front. And this means that alpha squared should be equal to 1, and there are only two possibilities, +1 and -1. So this, formality tells you that there are two types of time reversal. So now let's consider these two types in more detail, and when we consider it separately, so we consider this case and this case, and this case is realized when K is equal to 1. And then your time reversal is simply complex conjugated, and if I take complex conjugated twice, I will get +1. And this is the case of the usual, elementary quantum mechanics where your wave function is scalar. But then there is another situation where it is -1, and then it is easy to show that the corresponding K, because K is where, K is here. So this was the general ansatz, and the corresponding K is a matrix like that, and then when I write Okay, and then when I write K, C, K, C, as I said, this will be K by K complex conjugated, but K is real, and so it will be K squared, and this is time reversal squared, and K squared is equal to -1. So this is the second case, and the physical meaning of that is very simple. So this matrix flips the spin one half. So therefore we can say that the second type of complex conjugation it applies to the case of spinor with the spin one half. And not only to spinor, it is possible to show that also for many body system which which spin is half integer, then you can this type of time reversal. When the spin is integer including 0, then you have this type of time reversal. So that is the two types of time reversal. And also there could be a situation where there's no time reversal whatsoever. So we have three universality classes. We have a class where time reversal squared is 1, we have a class where time reversal squared is -1, and we have no time reversal whatsoever. So we have three classes. And these are the famous 3 Dyson symmetry classes with which until, I don't remember exactly, until 2000 probably, were the only classes known in literature. But then there was a very famous work of Martin Zimbauer and Alex Alton who have shown that in fact these 3 classes can be extended to 10. And this is what we will do. I will show you how this extension works. But the Dyson 3 symmetry classes are these. And now let us see what is the constraint that this time reversal symmetry imposes. So time reversal symmetry means the following: that if I apply time reversal operator to H in this way, then I will get the same H. So this is the non-quantum mechanical definition of time reversal symmetry. And now if I have time reversal squared equal +1, so time reversal is simply complex conjugation, then I write this and I obtain that H is equal to H complex conjugated. That means that it is a real Hamiltonian. So the first type of time reversal symmetry is the real Hamiltonian. Now, this class is known as the orthogonal ensemble. Why orthogonal? Because the corresponding U matrix that diagonalizes the Hamiltonian is a unitary real matrix, and such matrix is known as orthogonal matrix. And therefore, this situation is known as the orthogonal ensemble. Now, when, as I told you today, when we have a real Hamiltonian, then we have only one real number describing this thing, and then we have the square root of the determinant, which is a modulus of En minus En. So when we have, and this corresponds to orthogonal ensemble, because when ensemble is orthogonal, matrix H is real, then matrices that diagonalize it are also real, and then these are real. So then, if we write this distribution determinant in this way, or we write here generally En minus En to beta, where beta may be equal to 1 or 2. So this will be the orthogonal ensemble, and this will be the complex matrix. Complex matrix is total lack of time reversal symmetry. So we have two values of the Dyson parameter beta. So one corresponds to orthogonal ensemble, the other to the lack of any time reversal. And then let's study the second time reversal option. So then I simply again do a very simple exercise. Since now we have a spinor system, then the entry actually of the matrix will be by itself 2 by 2 matrix, and this any 2 by 2 matrix can be decomposed in unity and Pauli matrices sigma x, sigma y, and sigma z. But here, for convenience, I define, I write here the imaginary unit I and I. And the set of such things, unity 2 by 2 matrix, and then I sigma alpha equal 1, 2, or 3, this object is known as quaternions. And this is the definition of what why quaternions, because there are 4 of them. And so I can express any entry of the Hamiltonian as a combination of such linear combination of such quaternions, introducing the amplitudes H0, H1, H2, and H3. And this is simply the complex number. This is a matrix, unity is also a matrix, but these are complex numbers. And then what I have to do, I have to apply to such Hamiltonian the time reversal transformation, and time reversal is k times c, and then the conjugated part, which is c times k dagger, and this will be the transformed H, and by time reversal symmetry, it should be equal to H. So this guy should be equal to H. And now we want to know what kind of constraint it imposes on this H0, H1, H2, and H3. So as I said, CHC is simply complex conjugation of H. And then what I have is then there is K dagger, and K dagger, since K is, I remind you, 0, 0, 1 minus 1, then K dagger is minus K. And so this sign minus appears here. And now I have to take this H, make complex conjugation, and then apply K from the left and from the right. This is a very simple operation because this K is proportional to sigma y matrix, and we know how sigma y commutes or anti-commutes with all the other matrices. So when I do this simple operation, the result is also quite simple. So I will obtain the same form as the initial H, but with complex conjugated amplitudes. So, you know, on the way there will be different signs here, but then in the end, you will get this. And so, the time reversal symmetry then tells that this guy should be equal to that guy. And this means that all these coefficients must be real. So you see, in the case of simple time reversal symmetry, the Hamiltonian must be real. And here, it is not Hamiltonian which must be real, but the coefficients of expansion in terms of the quaternions. And that's why this I is written here, because if I will not write it here, then the signs here will start to dance, and it is much nicer to define quaternions with I, and then your time reversal symmetry will mean simply that your entry should be a real quaternion. So they are expanded in terms of quaternions with real coefficients. This is the constraint to the Hamiltonian. And then let us see, you know, some consequences of all this thing. So first of all, as I said, usual time reversal symmetry, the Hamiltonian is real, and that is it. So what actually follows from that? So if you have a real symmetric matrix, then we know that all the eigenvalues of such matrices are real up to the phase. So the eigenvector is a real vector times eta I alpha. So up to some global phase, which can always be made equal to 1, you have the real eigenvector. And that is easy to show because you have a real matrix, and then what you have to do, you have to write the matrix which is H minus E n times unity, and then take the determinant of that, and if this determinant is 0, then you find an eigenvalue, and then you simply do the following. You put one element of your eigenvector, let's say this one is equal to 1, and all the others you determine from the linear equation h minus e n times unity, but you take one equation less because one condition is already there. And so we know that that solutions of that equation is some delta, let's say delta n by delta solution of linear equation. And this is the full determinant, and this is the determinant with one reduced determinant, and both of them are real. That's why in this way you obtain a real with eigenvector, and this eigenvector is unique in the sense that it could have some occasional degeneracy, but there is no any persistent degeneracy. So you know, in general, all the states of this real Hamiltonian, all eigenvectors are real, and the states are not degenerate. And this is the general situation. Now, this is not the case for the second type of time reversal symmetry. So what I do the following. I take this time reversal operation. This is the time reversal operation on H. So this is the same as H, and this is the eigenvector. Okay, so this is simply this equality is time reversal symmetry. Now, then what I write this Schrödinger equation, and then I complex conjugate this Schrödinger equation. If I complex conjugate, K is real, double conjugation of H is H, and psi become psi conjugated. Eigenvalue is real, so it remains as it was, but psi become complex conjugated. And then what I can do, I can multiply this relation by K, let's say from the left, and use that K squared is minus 1. So this minus disappears, and I have H times K psi, and here is K psi conjugated, and what I obtain that if psi is an eigenvector of the Hamiltonian H, which is time reversal symmetric, then K times psi conjugated is also the eigenvector which corresponds to the same eigenvalue. And this means that the state is 2 times degenerate. So psi and K psi complex conjugated correspond to the same energies. So this is physically a very simple statement. So what is k times psi conjugated? This is simply time reversal transform psi, because time reversal transformation is k times c. So this is time reversal transform psi and psi. So the time reversal symmetry tells you that psi and time reversal transform psi have the same eigenvalue. And now there is very important point, and this point the following. It is necessary to show that these two eigenvectors, these two states, are not identical, because it could be that they are simply identical and then there's no degeneracy. So in order to show that they are not identical, we make some proof. Assuming the opposite, and assume that this one is proportional to psi, and this means that the states are identical, and these are just some number. Now again, some simple algebra, and what we do, we impose time reversal to this. So I multiply it by k times c. If then the result will be k squared times psi, because complex conjugation removes this star and k becomes k squared. And here, when I do the time reversal transformation, then this complex conjugation makes stars here, and also k appears. And then I apply this the second time. So I write this guy like lambda times psi, and then I obtain this. So you see what I on the other hand, k squared is minus 1. So on the other hand, it is this. So what I obtain that lambda squared times psi is minus psi. And since this is a modulus, it is positive, then the only solution is psi equal to 0. So this, but this is not a state. Therefore, we have shown that the assumption that these things are proportional to each other is wrong, because in the end we will get that it is not a state, because psi equals 0 is not a state. So it is a proof that psi and psi time reversal, which is this, they are two different states, and yet they have the same energy, the same eigenvalue. And this means that there is a 2 times degeneracy in the system, and it is very general. Any system which possesses the time reversal symmetry of the second kind, where t squared is equal to minus 1, they have 2 times degenerate eigenvalues. And there is also a different consequence, more physical, of that. this more physical consequence is the following: that suppose I consider this simple situation. Then, as I said, the eigenfunctions are all real up to in non-important phase factor, global, all elements of the same for all elements of eigenvector. So it is not important. Now, if we have a real wave function, then we cannot have a current because the current is the integral of I psi complex conjugation psi. Okay, and then if the function is real, then it is 1/2 of gradient of psi squared, and then here there is a integration, and the whole integral goes to the boundary, and if there's no current through the boundary, there is no current whatsoever. So this is the consequence of the real Hamiltonian. Now, when the Hamiltonian is not real, then this is not true. So what in this case it is not true, because what you can do the following: you can make an orbital current flowing this way and let's say spin up, but you can also have an orbital current that goes other way and spin down, and this is essentially these two states which are not the same. So there could be an orbital current in this case. Okay, it is interesting that that this has some physical consequence which is in principle possible to measure. So in the rest of 10-15 minutes I tell you some story which is much more physical than all this derivation. So the story is the following. This story is about so-called persistent current in the case where there is no voltage applied. So suppose you have a ring, and there is some random potential in this ring, and so on. This ring may be thick enough, and what actually was in fact surprising to many people of condensed matter, because people used to think that the current in condensed matter flows only if the voltage is applied. But it is not in fact the case, because what we know the following, that if the energy of your system depends on the applied flux, and here there is some magnetic field, constant magnetic field applied, right? Then the energy may is dependent on the flux, and then the current is simply the derivative of the energy with respect to the flux, because current coupled to the flux. In the Hamiltonian, we have current times flux to the linear approximation. So So if you have dependence of the energy on the flux, then you have some current without any electric field. So it is an equilibrium current. It does not produce any dissipation, doesn't produce any heat. And that, you know, for it is actually Rothschild and Butica from IBM suggested this normal state persistent current, and there was a discussion for some years where is the mistake, and there was no mistake. So then this persistent current was observed. So there was an experiment where people have a sample in which there were many rings like this of micron size, and then magnetic field was applied, and then it was possible to see that such sample when magnetic field applies has a different impedance compared to the case where magnetic field is not applied. Because if you have some current, so there is some magnetization, right? And this magnetization reflects itself in particular in the resonance properties of this stuff if it is put in the resonator. So there is a shift of the resonant energy, and it is possible to measure such current. And it was measured, although very small. And then usually this current behaves like this. It is periodic in the flux with the periodicity which could be flux quantum or half of flux quantum. So you know, the general Pomaronov effect tells you that in such systems there is a fundamental periodicity with the quantum of magnetic flux. But of course, there are higher harmonics. So there are periods which are twice shorter, 3 times shorter, and so on. And it appears that when there are many such rings, the current actually is flowing because flux breaks time reversal symmetry. But it is random. It can be one side or the other side. So there is a fluctuation of the sign and fluctuation of the amplitude of this current. And when there are many such rings, so the first harmonics cancels out. I mean, it is averaged out. It doesn't cancel out, it's averaged out. But the second harmonic survives. And it was, second harmonic means this periodicity, and it was measured. Now, what actually I want to say, so far it is all about potential scattering. So it is a case where there is no spin. And nevertheless, this current appears because flux breaks time reversal symmetry, and current, if you have zero flux, then current is zero, according to what I told from the very beginning, that if you have a real wave function, then there is no current. Now, but this dependence on the flux of energy, it is some energy without the flux, plus at small flux, plus phi squared. And when I differentiate it with respect to flux, then the current will be linear in the flux. Okay, the current will be linear in the flux. But now consider this case when there is a spin. Then, as I said, in the absence of the flux, where time reversal symmetry is preserved, in the absence of the flux, there might be a current. Okay? But if the current is in the absence of the flux, then applying the flux, I add something to the energy, but what I add is proportional to modulus of flux and not to the square of the flux. And this non-analyticity, it manifests the following, that that in the absence of the flux, there is some current, and then when I apply the flux, then it makes the shift of the energy, which is current times flux, linear shift in the energy. But current itself, and this shift depends on if you look carefully at what energy should be an even function of the flux. This means that it is only possible when there are currents in one direction and the currents in the other direction. And this is exactly what I have shown when there is the ring, and there is current like this and there is current like that, but spins are in different directions. So, if I differentiate it with respect to flux, what I will get a jump here. I will get a jump. It will be theta function of the flux. So it is plus one for. It is not theta function. It is sine function. Current should be even function. So it is. It will be a jump. So then this consistent current which we will observe, it will not behave like this as a regular function with some linear slope here. It will behave like there will be a jump here, then some smooth behavior, then jump again, then smooth behavior, then jump again. And this thing, of course, this is at zero temperature. When temperature is not zero, then it will be smoothened somehow. But this jump will be present. This slope at zero temperature is infinity. At finite temperature, it will be something finite, but increasing with decreasing the temperature. And this is the manifestation of the Kravtsov degeneracy, because this Kravtsov degeneracy and the presence of the flux, or of the current, without breaking the time reversal symmetry, it is all related. And physically, one of the manifestation of that is that persistent current is not a regular function, but the function, a Sol-like function with the jumps. So this is one. I did it very briefly because this is, so to say, star question. It is beyond the scope of the lecture, but it is showing that actually everything that is related with the symmetry, everything which is related with this random matrix stuff, it has some physical, clear physical picture and clear physical implication. So it is 5 minutes left. I think I will stop here. And next time we will be extending this